Welcome to the September Cardano R&D session on Ouroboros. My name's Fergie Miller. I'm the Director of Research Partnerships at Input Output, and I'm delighted to welcome you to what is actually our fourth Cardano R&D session. These sessions are hosted in association with the Research Working Group at Intersect, which the Input Output research team helped set up. We have two fantastic speakers today for what I think will probably be our best session yet. We've got Aggelos Kies, Chief Scientist at Input Output, who will be presenting Ouroboros and Mega. That's the research area that is proposed under Cardano Vision and which will take the Ouroboros protocol through to its final form. We also have the Laos innovation team led by William Wolf, who will be providing a comprehensive update as they hand over Laos to the IO engineering team, which is a key milestone in its development. These Cardano R&D sessions were developed in response to community feedback, and they bring the Cardano community together each month to explore research-led thematic discussions that bridge the gap between research and development. This session has actually been delayed slightly from after the summer, but they typically take place on the first Tuesday of each month. And on the 7th of October, we'll be hosting the next Cardano R&D session on interchains. Before I hand over to Aggelos, I just wanted to provide a quick refresher for everyone. So I hope you can see my slides. The work program 2025 that has been funded by the Cardano Treasury is actually the first year of a 5-year research program called Cardano Vision that really looks through to 2030. It's governed by a strategic research agenda, which really outlines how IO builds systems. Underneath that, we have a vision statement, which covers 9 thematic focus areas, and that's broken down into 34 individual research streams. And from that then stem individual annual or biannual work programs, where we bring forward and prioritize a number of research streams and technology validation streams. This conforms to our evidence-based methodology, which I hope a lot of you are familiar with. So in research, we often operate a good few years away from market, typically 3 to 5 years, and we will over a year or two publish a paper or a series of papers within a research stream, and we will support those papers with technical artifacts. And that really originates from an initial problem statement and is in line with first principles thinking. We then hand over that stream to an innovation team that do technology validation. They will prototype, they will formally prove the maths. They will develop any supportive tooling, and they will provide specifications for that initiative to then be handed over to an engineering team to implement all the way through to launch and mainnet. And those streams are supported throughout by research and innovation all the way through to launch. The vision covers 9 focus areas, from the world's operating system here at the top, smart contracts, Ouroboros, what we're talking today, but also tokenomics, identity, democracy, layer 2 scaling, Hydra, interchains, zero knowledge, and post-quantum. So it's a big body of work, a very rich body of work, and Also, I just wanted to bring your attention. We've committed to milestone reporting twice each year, once mid-year and once at the end of the year. We've just finalized our consultation period with the community around our mid-year report. So we will be posting those final documents up on the Cardano forum, which we're increasingly disseminating to, along with the sort of write-up of this session today. So I just wanted to bring that to your attention. It's a very rich report, both on the research side and on the technology validation side, which should bring everyone up to speed with all the great work that the two teams are doing. So that's enough from me. I'll stop there, and Aggelos, I'm delighted to hand over to you.
Great, yeah, thanks Fergie. And we can start discussing Ouroboros Omega. So I think it's fitting, before we go into what we do in the future, to look a little bit about what happened in the past. So what was Ouroboros, how it started, what were the guiding principles? So I was working in proof of stake more than 10 years ago. That was before actually I was involved in the Cardano project. And it was at the time that still early on, let's say, if you think about it in the general picture of blockchain technology, a lot of things have happened in the last 10 years, and very importantly, Cardano was launched, and Ouroboros became its backbone, and it was designed and developed as a system. So what was the guiding principle then? The guiding principle was that we did have Bitcoin. The Bitcoin was secure, decentralized. It was the inspiration for a lot of other systems, including Ethereum. But it was energy inefficient. I mean, it had a lot of good features. It was secure and decentralized. But the energy inefficiency was critical, and was a critical deficiency. And there was a lot of other things that you might want to improve, but this was something that was highly motivating at the time to try to see if it can be changed and improved upon. So the objective then was to try to retain all its fundamental, or as many as possible of its fundamental properties, or even try to strengthen them. For example, its security, its decentralization, and so forth. But while doing so, while substituting proof of work with proof of stake. So basically substituting a physical resource, which is spent in the case of Bitcoin, with a resource that's virtual, and it doesn't have necessarily to be spent when the protocol is operating. So this was the guiding principles behind the development of Ouroboros, and Ouroboros delivered. Not only delivered that, but delivered a lot of fundamental improvements. So just to give an example of some of the concepts that were retained from the Bitcoin blockchain. So one important feature of the Bitcoin blockchain is its dynamic availability. So that's a concept actually that was formalized by our team. Dynamic availability basically means that you can get consensus despite the fact that the nodes that are operating the system are transiently available. So they come and go. They're not available all the time, and their number can actually fluctuate over time. So Bitcoin was a remarkable protocol managing to provide consensus in such a setting of dynamic availability, and this was actually a property that was never achieved before by classical consensus protocols that essentially operated under the assumption that you have like a fixed set of nodes. Of course, some of them might be adversarial, but it was not meant to handle wide fluctuations of participation, both in terms of nodes entering the system as well as in terms of nodes exiting the system. So Ouroboros is a protocol that achieves dynamic availability in pretty much a similar fashion, in a way that Bitcoin achieves it, and it also achieves other properties as well that are characteristics of Bitcoin. For instance, the ability of Bitcoin to self-heal when it finds itself in a situation which is which suffers a major consistency violation. So this is also the case for Ouroboros, and this self-healing property is also a property that classical consensus protocols cannot achieve. So in many ways, we were able to port a lot of these properties into the proof of stake world, and on top of that, it was also possible to improve on aspects of the protocol operation. For instance, decentralization, despite the fact that is present and a characteristic and feature, and an advertised feature, if you want, of the Bitcoin blockchain, what is observed in the practice of the protocol is that you get this resource pooling. So you have these centralization forces that make participants pool resources together and then operate as a single entity, having essentially centralized operators managing a large amount of resources. So this was something we wanted to avoid, and we wanted to be able to reach to be able to make the protocol reach a more decentralized state compared to, let's say, the profile that you would get in the Bitcoin blockchain operation. And this was achieved by a reward sharing scheme. So this gave a highly decentralized profile for the Ouroboros chain. So this was something that, like an example of how we went well beyond of the security and decentralization profile that Bitcoin would provide. Another example of a similar nature is the way we deal with time. Now, these protocols, or these resource-based protocols, fundamentally rely on time synchronization. And in the case of Bitcoin, being able to synchronize on time is fundamental to be able to adjust the difficulty so that the protocol remains stable in this dynamic availability setting. And similarly, for proof of stake protocols, you have these sequences of lotteries that enable the protocol to make progress. And being able to synchronize clocks is another fundamental precondition to be able to reach consensus via proof of stake. So you want to remove dependencies on time. And this is, for instance, a problem that we tackled with the Ouroboros Chronos protocol that we published 5 years ago. So that's another case where we demonstrated how the protocol itself can be a synchronization tool, and we have achieved that with under a set of assumptions that went well beyond the assumptions that enable Bitcoin to provide synchronization. So in many ways, Ouroboros brought into the proof of stake setting the security and reliability of the Bitcoin blockchain and improved it in a number of directions, such as time and clock dependency and decentralization. But there's still a lot of things that we want to achieve. So now, and I'm going to come now to looking ahead. The approach that I want to advocate in the context of Omega is it will shift the guiding principles to two guiding principles, going well beyond what the Bitcoin blockchain achieved, and let's say how it can be improved. So the first guiding principle for Ouroboros Omega is realizing the fact that the state of being distributed can be a disadvantage, right? So a distributed system can always be at a fundamental disadvantage compared to a centralized system, in the sense that it has to provide a functionality, but it's not capable of making, let's say, the optimal decision, because it doesn't have all the information. And because it's comprised of many nodes, it has the penalty of coordinating these nodes and making all these different nodes provide the same type of service in the view, let's say, of a client, despite the fact that some of these nodes might be malfunctioning. So that's the reason these consensus protocols are so complicated. It is exactly because they have to, somehow suffer the penalty of being decentralized or being distributed. And you can see that, let's say, in the design of Bitcoin. There's a lot of penalty, let's say, in the design of Bitcoin that comes exactly because of the fact that the protocol is decentralized. However, if you look at the classical distributed systems literature, you can see that the guiding principle that is used in the classical works is that you design, in order to achieve high performance, you have to have multiple execution paths in the way the protocol operates. And by multiple execution paths, I mean the following. The protocol, if the protocol detects and finds itself in optimistic, like in good conditions, so its environment, let's say, it's ideal for fast performance, whatever that might be, then it delivers a service which is as efficient as possible. So basically, it gives you like the optimal type of operation, the one, let's say, that you could achieve if you had a super powerful centralized system. So essentially, the distributed penalty is eliminated. And that's because the conditions of the environment are right. So basically, all the nodes in the network are, they have like near 99.9 uptime, and there's no network splits or anything like this. So the system then enters an execution path, which is blazingly fast because it detects that the environment is good and it can deliver the service that is essentially optimal for this set of conditions. But then, if something happens, let's say some nodes fail, the network splits, like you have like a bad event happens, then the system can fall back to a lower performance execution path. So the guiding principle for Ouroboros Omega now, the one that is advocated in this research direction, is like to develop these highly decentralized systems with the ability to exploit the potential for performance whenever that potential exists in their operating environment, right? So in other words, if you see high uptime, if you see the network is well, the protocol should accelerate and should perform in the optimal way, given the way that the optimal way that its environment allows, without though sacrificing security. And that's the key point. And that's why Ouroboros Omega is a good direction, because we do have the foundation now. We do have the foundation of Ouroboros, which is a highly decentralized and secure protocol. And now the question is, how do we exploit that secure foundation so that we accelerate and we improve any performance indicator that we care about when the protocol can find the opportunity to do so? And you see there's two examples already of this that are explored and are detailed within the Cardano Vision plan. So one example is the Ouroboros Peras line, and another example is the Ouroboros Lia. So these are two, Lias and Peras are two examples that exemplify how we take the guiding principle that I just said and we put it to work for the protocol. So in both cases, what you have is when the protocol realizes that there are conditions available for high throughput, it goes up, increases its production to fully absorb the throughput that is available. So this is the sort of the objective that we had when we were designing LEOs. And when things are not as good, when conditions are realized that are not optimal, then the protocol can still provide the level of security that you get with Ouroboros now. So there's this fallback. And the same thing, a similar thing happens with Peras in terms of settlement time. So when the conditions are right, the settlement is accelerated. And then when the conditions become not suitable, then you again fall back to the secure operation that you have at the basic Ouroboros operating environment. So this is the first guiding principle that you have already two examples of it, but it permeates the whole logic behind Omega. So Omega basically says we exploit all acceleration and performance as well as security improvements that are feasible if the operating environment allows us to do so, but we do not do that at the expense of security. So the protocol can always detect when things are wrong, and it falls back to safe, decentralized operation that may be less performant where things are bad. And this, what I just said, I gave two examples on security, but you can also think about it in terms of security. So fair transaction processing is such an example, right? So fair transaction processing is something that is a security improvement, is the ability of a protocol to provide fairness for transaction processing. Observe that in a centralized setting, if you have a trusted third party, it is easy to get fairness because everybody submits their transactions to the trusted third party, and then the trusted third party can serialize the transactions in a fair order, following the order, let's say, that the transactions are received. The problem with distributed protocols is that it's not possible to do that anymore. It's even hard to say what is the absolute fair order, right? Because there's not a single recipient that gets all transactions to say, I've received transaction 1, 2, and 3 in this order, and thus they should be processed in this way. In the distributed system, things are actually much harder. But if you have a really high-performing operating environment, you can exploit that to provide fairness. And now you want to make sure that when things are not operating as optimally as possible, you want to still fall back to perhaps a less ideal version of fairness, but a version of fairness that is still sound. And this is based on research that we've already performed and research that I'm looking forward to see it manifest itself in the context of Ouroboros. So this completes my short summary about the first guiding principle for Ouroboros Omega. And then there is a second guiding principle that touches on the topic of resources. So all these protocols that we talk about, the Bitcoin blockchain, Ouroboros, as well as other protocols that people are running, for example, the Ethereum proof of stake protocol, these are resource-based protocols, which means that you participate because you have resources of some type. The highlight here is that this should be contrasted with classical distributed systems protocols that enable you to participate if someone has authorized you to be a participant. So this is the permissioned, let's say, aspect of classical consensus protocols versus the permissionless aspect of modern consensus protocols. But the issue here is like what type of resource is relevant. And this is the second guiding principle that I have about Ouroboros Omegas. Currently, Ouroboros is a pure proof of stake protocol in a way, right? So you have stake, you have ADA, you can participate, and the more ADA you have, the more influence you have on the protocol. But I think we should increasingly look beyond, and this is not just for the consensus side, but it's also for other functions of the protocol, like the governance of the protocol. We should look beyond of pure stake operation in order to secure these protocols, in order for them to be robust. And what's the reason for that? The reason is that any of these resource-based protocols, they would suffer attacks if someone is able to exert a lot of influence in the resource that the protocol is using. So going forward with a multi-resource logic will enable not only to have a more inclusive participation in these protocols, but also have a more secure and reliable profile. So this is the second guiding principle, like looking deeply at the type of resources that are available for securing these protocols and diversifying them. So, and for me, this is another important direction forward, right? So a diversified resource portfolio is something that you want to have in a system that is resilient and sustainable for for a long-term operation, as we would like the Cardano blockchain to be. So with this, I think like I covered the main elements of what I wanted to touch on, and I'll give it back to Fergie to see if there's any questions that any of you have.
Yeah, thank you, Aggelos. So we have we're working on Google Meet today. So we have the meeting tools button down in the bottom right, which is 9 dots. And within there is a Q&A tool. So if you have a question, please could you submit it via that tool, and we look forward to a couple of those coming in. Aggelos, like I've just got one question while we wait for that. Are these two guiding principles, are they always complementary, or are there sort of scenarios or situations where you might have to compensate on one versus sort of compensate on the other, as it were?
Yeah, good question. Yeah, I would like to think they can be made complementary, but yeah. So my take on this is that they can be complementary. They can coexist in a final system, but the devil is in the detail as always, and we need to do the research to be able to answer this question fully. But my thinking right now is that they can be complementary, and we can be in a multi-resource environment that exploits any optimization opportunity that it can.
Okay, great. And I've got one from Jesus here. So what are the main types of different resources that will be or are being considered for a mega state computation space, or is it something else entirely?
Yeah, so it's a good question. So useful work is definitely one of the things that we have discussed, and by useful work, this is to be contrasted with proof of work in the case of Bitcoin. So Bitcoin does basically useless work. I mean, useless in terms of it's useful in the context of Bitcoin, but it's useful only in the context of Bitcoin security, but it's not useful, let's say, for anything else. And we have done already the preliminary research on that, showing that you can actually have work that is useful, fundamentally useful in its own right, and still repurpose it for security in the context of consensus. So for instance, you could have work that requires calculating a difficult protein folding problem, or work that calculates a complex zero-knowledge proof, and also repurpose that work for consensus building. So that's a type of resource that I consider in scope for this, and we have it in the research agenda. But you can also, I mean, this gives you an example of a physical resource. And again, like the point here is that we don't want to be wasting any cycles. We don't want to be wasting any resources that we're not interested in investing anyway. Right? So useful work basically says computational resources are to be invested, but these are fundamentally needed anyway. These are things we want to be doing anyway. And then additionally, in addition to the fact that we want to be investing this anyway, we can also repurpose them for securing the consensus infrastructure. So this is an example, but then you have other examples of virtual resources as well. So for instance, reputation is another example that is intriguing and interesting to consider. And by reputations here means the things that people do and their attributes of their online identity that are things that people, it is essentially the contributions of members of the community to the community itself as recognized within their digital identity. And this is also something that I think could be an amazing resource to be able to incorporate into the consensus infrastructure. It's already to some degree incorporated as part of Voltaire with the DREP program, but that's only a first step of how this resource could be used by the Cardano system.
Great, thank you. And we've got a second question here from Andrea. So many thanks, Aggelos. Could you elaborate a bit further on the trade-off between limited knowledge in decentralized systems and the capacity to recognize the state of the network and adapt consequently? He says it sounds quite challenging.
Well, it sounds, I agree. It's very challenging, but that's why we're here and that's why we're doing research. If I was telling you that this was a solved problem and we know how to do it, and then we would be talking about an engineering project that we are going to build it. But yeah, I totally agree, and what you say is spot on, Andrea. It's a very challenging problem, but it's a problem that I'm hoping we're able to solve. Like, will we be able to solve every instance of this? Like, we'll have to see, right? So good progress is already being made. I think Leos and Peras are good examples of what can be achieved. The objective of Omega is to actually fully explore that space and see whether we can solve it without giving up security. And then in cases, I'm not anticipating that we're able to solve everything, but by not solving something, what I want to be doing is like getting a proof that that's impossible, right? So either we achieve something or we prove it's not possible to achieve at the level of security we want. And in that case, like we know that we've completely characterized the design space, right? So we either achieve it or we know it's impossible. And then we know what we can move on to the engineering phase and deploy it as part of the system, assuming and by we here I mean the Cardano community in a collective way.
Okay, so we've got another question here from James and a few more as well. So will we see a slow ramp up of TPS? You've seen that we can expect up to 1,000 TPS, but of course, with this fact, we can have many transactions within a single transaction. What, in your mind, what will the layer 1 be able to handle as a sort of ballpark figure?
Yeah, so I shouldn't actually comment on any specific numbers at this point because it's still an ongoing research. Is an ongoing. I mean, Leos we already have one output, but it's still an ongoing research and prototyping effort to nail everything down. But increasing the TPS, I should also point out, measuring the TPS is also part of our research agenda because, like, TPS measurement in itself is a very difficult problem, right? So, and one transaction in Cardano does not necessarily mean is the same as one Visa transaction or one Ethereum transaction, right? So these are completely different objects, and finding the right measure for TPS is part of the research agenda. It's not part of Ouroboros Omega, but you'll find it in the decision toolset. Part of the Cardano vision. But now, this being said, going back to this, we want to measure correctly and first principles, and And absolutely, you will see a ramp up of TPS. Now, to what degree this can be achieved? Again, this is not something that, I can say a concrete number right now, but what is the research plan for Ouroboros Omega is to try to get as fast as possible, right? Try to approximate basically what you would get from a centralized system that is able to have high throughput and high response time. Now, this being said, layer 1 is only going to be one dimension of how Cardano is going to work. And I do think that layer 2 solutions as well will be part of the picture about how we cover completely this design space. So layer 2 protocols, and I'm not talking just about the Hydra head protocol, which is available now, but we do have a lot of other layer 2 directions that explore the design space of layer 2 operation that will also make it feasible to go to extremely high TPSs. So my take on this is that if it's something that can be done on the internet, it should be able to be done. That's it. So in other words, there soon be a use case that anybody has in mind that has a certain requirement on TPS, and it's feasible to run it as an internet service. And that's not possible to do it on the Cardano infrastructure. It should be doable on the Cardano infrastructure, either on layer 1 or with the right layer 2 deployment.
Great. We're just going to sort of try and squeeze in one or two more questions. So Rusty says, can't a malicious entity always ruin the optimistic environment to force a fallback to slower consensus? How resilient is the optimistic environment?
Yeah, I love that question. It's a fantastic question. I mean, this is the type of thing, like, that I'm thinking, let's say, when I'm, before going to bed, or like, this is like the type of questions, that I will love to work on. It's a fantastic question. And I think it kind of actually points exactly at one of the issues of these multiple path systems, right? So, there are many ways you can design like this dual execution path, right? You can say, I have this super optimistic path, which is amazing. And then like once bad things happen, the protocol falls back to some like really slow operation. And of course, the very important question is, what is the trigger? And you can even ask like how many levels perhaps, like perhaps there's multiple levels. It doesn't have to be 2 paths, right? So 2 paths is the minimum, but you can have 3, let's say. But of course, it's a very stupid system, one that is like very optimistic, like, this completely optimistic system that is perfect, but then, anyone like, can just hit the wrong button on their keyboard and suddenly the system says, oh God, like now I cannot handle it, right? So I have to go back. So we're aware, I mean, this is the type of problem we're working on. Of course, we want to develop systems that, interpret optimism in a sort of as relaxed way as possible, right? So, so trying to do this right is difficult, but, it's up to the exact design, right? So we are working exactly on these questions. These are the type of questions we're aware of. This is why research is needed. And finding the right balance between like what optimistic means and when fallback is triggered is a difficult question, but this is exactly why we do the research, and we try to basically optimize this so that it's not fragile. So to finish this answer, we don't want fragile optimism, right? So we want to have like a reasonably robust optimism.
Great. And then Alex, if Omega has maximum throughput when the system is operating optimally, what prevents lazy or adversarial nodes from slowing down the system? Yeah,
so I mean, first of all, you cannot. I mean, there's no way to avoid in a truly decentralized system. You cannot prevent people doing whatever they want with a node they have, right? So ultimately, you have a sort of a rational kind of setup, right? So people should invest throughput into the system because they want to, and they are incentivized to do so. So nothing prevents them if they're lazy or adversarial, but of course they're hurting. They by doing so, they would be hurting their sort of the rewards that they receive from the system, right? So part of the design obviously is not just to be able to tolerate Byzantine adversaries, but also align the nodes running the protocol, so-called honest node, with the right incentives. So they're not just honest, they are rationally honest, right? So they follow the protocol because it makes sense for them rationally to do so.
Great. And then one last one. Zhao, I hope I pronounced your name right. Will Omega, in seeking better performance, allow each transaction to have a greater volume of information contained within it?
Yeah, I would say that's a possibility, right? So how much each transaction can carry, how much every transaction can carry information is something that can be calibrated and adjusted. It's all a matter of, how much bandwidth basically you have available for transactions to go through. So that's a possibility.
Great. So I think we'll leave it there. Mark, I don't know if you want to take this one, Aglos, but I was going to leave it. Actually, we'll take it now. What is the tight bottleneck resource in the formal Leos in Omega analysis? And can you state the resulting scaling or settlement bounds explicitly?
Yeah, I'm not sure I fully understand the whole aspect of the question, but perhaps I should just quickly say that, Leos is being researched as we speak. We have the first paper out, the analysis is there. We do have more work, prototyping work that is coming out. So it's an ongoing research project, and there's going to be, a lot of information that is available and will be coming up as more research is done. Okay,
great. So Aglos, thank you very much for your time today. I know you're a busy guy, but I was also told by one of the research team that you wouldn't be able to resist to talk about Ouroboros Omega. So we appreciate you coming on and imparting your knowledge.
William, thank you very much. Thank you guys.
Thanks, William. I'll now hand the floor over to you, and along with Georgios and Brian, and look forward to your presentation on Leos.
Sure, thank you. And welcome everyone. We prepared a short slide show here to have people follow us. My name is William, so I'll walk you through the Ouroboros Leos, why we need it, and the challenge we face with the current system, and how this proposal sets us up for the future. And I also have Brian and Jurgis with me, who will later explain how the protocol works and what kind of evidence we have, how well it works based on our simulations. So, but first, before we dive into the technical part, I would briefly want to highlight the core team behind Leos. So these are the people who have been designing, simulating, and shaping the protocol over the last year, and their dedication has been essential to getting us here. So therefore, I want to give credit where credit is due, and I just want to underline that this has been truly a collaborative effort, and across many fields and organizations. So it took, as you can see, many software engineers, form engineers, researchers, and prototyping, along with the support from external parties. So it's basically a combination of skills and perspectives that made Leos possible. And with that, let me quickly walk you through the agenda. We have 4 points. I'll start with the why. So why the current system needs to change. As I said, Jurgis will then cover how it works, followed by Brian with some of the simulation analysis we've done, and I'll then return to kind of give a look forward in terms of where we go from here. Okay, so let's start with the first one. Why do we need Leos? And our starting point has basically been the CPS, the Cardano problem statement 18. And in short, it summarizes like 3 fundamental challenges. We have capacity, which is essentially that users are experiencing some degraded experience because of blocks filling up and seeing congestion and delays. The second one is kind of summarized as capability. So we see that certain scripts or smart contracts are hitting certain protocol limits, and or have to be designed within those bounds more and more, and that could be arguably a leading indicator for discouraged development for richer, more complex applications. And then lastly, the sustainability side of things. So most of the rewards currently come from the reserves and not transaction fees. And that's also arguably not a viable solution in the long term. So let's take a look at the first one. So this slide, we see what the first challenges here in the numbers. And the chart here to the right shows basically the block size distribution. And we have on the y-axis the number of blocks, and on the x-axis the size of blocks in bytes, all the way up to this red mark on the trailing edge, which basically resembles the maximum size or the current size of a parse block. And looking at the data here, we can see that the block utilization is for a number of blocks well above like 80 or 90%, like hitting or kind of cut off at this edge. So we have more and more congestion at this point where blocks are filled up and we have more demand essentially that is already pushing against the protocol limits. And the second one I want to quickly cover is basically transaction complexity limits. So here we see one of the two protocol parameters for Prius scripts, which is script memory and the number of steps, but we only look at memory here. And here the same applies. So we see more and more scripts here towards the tail that basically right at the memory bound. So we don't know the exact reason, but one could argue developers are basically optimizing to just kind of fit their complexity within these bounds, and more of these scripts are basically deployed instead of maybe freely innovating. So in other words, they're hitting a ceiling here as well. And then we have the sustainability side of things, so the depletion of reserves. And rewards today mostly come from reserves and not transaction fees. So you can see actually in the chart, this very thin red line is the part of the rewards that fees make up, and also the forecast towards the next couple of epochs or years. And this has obviously an effect on SPO profitability. So, by the way, all of these charts are available in the CPS. So I'm just kind of covering those here briefly as a starter. So on this chart, we basically shows like the situation of parse in the longer term. If we don't consider reserves, we basically see that the throughput of the TPS in TPS on the x-axis, and the rewards expansion ratio on the y-axis. And as I've shown in the previous slide, fees don't cover the costs, and profitability basically only comes from the subsidies. And what this chart illustrates is that parse throughput today isn't capable of delivering the kind of fees we would need in order to shift towards this green area, the profitable one. And that's exactly where Leos comes in and what Leos can unlock. So basically much higher transaction rates and essentially securing the ecosystem economically. So one may ask, why don't we just push these limits and increase maybe the size of blocks? And the problem is that parse wasn't designed for this. So larger blocks slow down diffusion and increase short forks, and also reduce like the chain security. So parse is basically designed to rely on silent periods. So we can't simply push the limits and actually need a new approach. And this is, again, where Leos comes in. And with that, I hand it over to Yogis, who will explain how the protocol works.
Yeah, thanks, Will. Hello, everyone. As Will said, we cannot make the blocks larger. So what's the idea? So the idea of linear Leos is to do something else, is to split blocks apart on a small part and a large part. The small part is what we call the ranking block, and you can think of it as being current route blocks. And the large part being the endorsement block, which is only including the chain optimistically. So if you want to go to the next one, Will. So when ranking blocks are created, and they're created with the same schedule as in Browse, they also announce and is it, you cannot hear me, you mean, or what?
Just the mic could be a bit clearer.
Oh, sorry. Just 1 second. Can you hear me now, maybe?
Yeah, that's better. Yeah.
Yeah, good, thanks. So when a ranking block is created, and these blocks are created according to the browse schedule, it also announces an endorsement block, a large block containing transactions. And the moment this is announced, a vote starts on the correctness of the transactions in the EB and their availability. And if the vote is successful, a certificate is created. And can I go to the next one, please? And this certificate now can only be included in the next block in the chain. Now, if the certificate is included in the chain, this signifies that the transactions in the EB are put exactly after the transactions in the previous ranking block. Now, by requiring that certificates can only be included in the next block, we're also ensuring that the order at which transactions in the EB were created is the same as the order they're found in the blockchain when they enter, if they enter the blockchain. They're not changing positions. They're always after the RB that announced that this EB. Can go to the next one, wait. Now, in case the vote fails and no certificate is created, the protocol can reverts to browse mode if you want, and the ranking blocks directly contain transactions. Further, to reduce work being lost, we have transactions in EBs included by reference. So the next block producer can re-include the same transactions found in the previous EB, and he only has to communicate the references, and he does not have to resend all the data. Can you go to the next one, Will, please? So in the end, what we get here is high throughput by exploring opportunities to increase throughput when ranking blocks are generated far apart. We get robustness as we downgrade to browse whenever network conditions are not favoring or ranking blocks are generated close apart. We get economic viability in the sense that Will mentioned, like by increasing throughput, we allow the amount of fees that can be gathered to be sufficient to fund the protocol and have profitable SPOs. And further, this protocol can still operate under the same reward scheme as browse, basically rewarding based on the performance factor. Yeah. And with that, I'll pass it to Brian to talk about the evidence gathering process.
Okay, thank you, and hello, everyone. So we're taking a very strongly evidence-based approach to assessing LAOS and also refining the protocol. So that's a lot of the work we've been doing over the past months. And one thing is, of course, we have the research paper, so that gives us theory that provides evidence for the viability of LAOS. But we've also done analytic calculations like probabilistic mathematics to look at, in theory, what would the precise efficiency of LAOS be. Some of you may be aware there's what's called delta QSD modeling analysis that has been done for Prowse. This is a technique for simulating network and other systems like LAOS. And we also have a Rust simulator and a Haskell prototype. So we have a nice toolbox that covers all the bases on seeing what LAOS could do and what it looks like it will do when it's fully implemented. The other thing we're looking at is looking at it under realistic conditions. So we've been doing simulations with mainnet-like transactions, either small ones or heavy Plutus ones, large metadata. There's a lot of variety of transactions on mainnet, and we wanted to make sure it could work no matter where the future load on the system goes, whatever mix of transactions we have there. And then in the simulators, these aren't just toy models. We're simulating for mainnet-like topologies. So we have simulations that are simulating 10,000 nodes, 2,500 block producers, 5,000 relays, and thousands of other nodes. We're using the realistic state distributions, realistic characterization of network connectivity, bandwidth, latency, things like that. And then also realistic timing for the cryptography. So we have a very robust and representative way of measuring the protocol, even prior to the engineering work being done on it being fully implemented. And then, of course, we're using these simulations and models to understand what are the realistic values and the optimal values of protocol parameters, what sort of resources the nodes might need, what happens when you push the protocol all the way to the limit, and then, of course, how does the protocol respond when it's being attacked. In the next chart, we're summarizing a lot of work we've been doing. So basically, much of the first half of this year, we were running dozens of simulations each week. And if you look at the CIP, you can see some of them, but we also have a technical report, the second technical report that goes through these. It has a big index of all the stuff we've looked at. So there's really a lot there. You can also view the past monthly meetings and the future monthly meetings, which we have archived. But the bottom line from all these experiments, basically more than 1,000 experiments, we've demonstrated that LEAS can work above 100 transactions per second. Of the average size transactions on mainnet, these are about 1,500 bytes per transaction. TPS isn't the best metric because not all transactions are equal. We prefer to talk about throughput in terms of kilobytes or megabytes per second on the network, and that could be big transactions or it could be small transactions. But the thing we're seeing is that in uncongested conditions, the average transaction reaches from the mempool to the ledger in about a minute. Of course, when block production, which we know is random, it's a little bit of unluckiness, that might be a little bit longer. But as a rule of thumb, about a minute to get to the ledger, and that's quite competitive with what's occurring in Praus. Under congestion, we have what occurs is called back pressure. And this is where clients need to hold off. They're actually told by the nodes to hold off submitting transactions. And then the nodes will grab more transactions from the clients as the congestion permits. So we run under those conditions, and inevitably, once you overload the system, you will see longer waiting times. But the really nice thing is that's all you see. You're not going to lose transactions. There's no danger to the protocol or anything like that. So it's a little bit like in the Praus world where there's an airdrop or something and blocks get full and you just have to wait a little bit longer. So even at LEAS's much higher transaction throughputs, that's the same sort of behavior. You see back pressure, some waiting, but the system stays safe. And then the other thing we have, we've measured the spatial efficiency, we're calling it, of LEAS. Like approximately 95% of the data that's stored in the ledger is the transactions. So there's only about 5% overhead and bookkeeping for things like the certificates and other hashes and other information. So we're effectively using disk. And in the next slide, we have a couple more points. One is that LEAS will let us raise the Plutus limits by quite a bit, perhaps even more than 100 times. That's going to depend on community decisions because you have to decide, is it individual transactions that should have higher limits, or do you want to raise the per block limits or some combination? So we have data on this for the community to help make a decision. And as the engineering team progresses, that will have more relevance to discuss what are appropriate Plutus limits. But the bottom line is they can be much larger, and that will help a number of use cases and dApps. The other thing is we're seeing when the system is under attack, when nodes are acting maliciously, trying to either interfere with the voting or with diffusion, for example. Generally, they're only affecting throughput. They're not affecting safety of the protocol. And they're only doing that in proportion to their stake. So an attacker with very little stake is just going to make the slightest epsilon of impact on the throughput. And this is the same as in Prouse, where if someone with a lot of stake decides not to make blocks, then Prouse throughput goes down. Same with LAIS. The other thing we were looking at, because we're sensitive to the real life deployment of LAIS, is what are the costs for SPOs. And so they're quite modest for LAIS at this level. It's really not a big difference from what existing SPOs are doing in terms of deployment and their monthly costs, except with higher throughput, there is more disk storage needed. So that's sort of inevitable. And the more you put on the ledger, the bigger is the ledger, and you have to pay those monthly bills. I know that the research program has thought about looking into things like pruning, compression, and other archiving and things like that. So someday there might be approaches to even reduce those costs. So I'm going to hand it back to Will.
Okay, thank you. Okay, then I'll cover real quick where we go from here. So looking ahead, we basically reached an important milestone. We're now at the handover to the engineering team, here marked in red. And our plan is to support them through the end of the year and make sure the transition is smooth and that they have everything they need. I also added this diagram here, which some of you may have seen before. It is part of the SIP rationale section. And what it essentially shows is a high-level comparison of Prouse in red here and our proposed layers, which we've described in the SIP, and the research paper version of layers. And it compares them on 4 different dimensions, like throughput, inclusion latency, the ecosystem impact or adaptation cost, and the time to market. I think that the main message here this carries is that going big on all 4 of them may achieve the highest throughput, but it also comes at an arguably large cost, whether that's a change in the user experience or further delayed delivery, such as time to market, which may even push some SPOs into like an unprofitable area, or adaptation costs, which affects builders and maintainers of tooling and such. So with the time given to us, we made this proposal that, in our opinion, makes a really good trade-off because it balances like the negative sides and still delivers a real increase for what we look for, which is higher throughput. And nevertheless, having spent most of last year simulating and testing the mechanisms described in the research paper, I want to say that work isn't lost. So it isn't the end of the story, but a step-by-step proposal of what we're doing here. And depending on when demand justifies it, we can add things like decoupled block production, recursive block referencing, or even sharding without overwhelming the ecosystem with costs before the benefits can be realized. And with that, thank you very much for listening. Here I've linked a couple more things like the website and the CRP for the curious, as well as the formal specification. And I want to just say, if you are interested in how things are moving along, Sebastian will take over our monthly meetings starting October 1st. And he will basically bring you up to speed on the latest and greatest of layers. Thank you.
Thank you, William, Georgios, and Brian. So we've got about 10 minutes or so left. So I'd invite those in the audience who wish to submit a question to do so, again, by the meeting tools icon in the bottom right of your screen. I guess whilst that happens, thinking about the number of simulations that you run, which is by no means small. I guess for the everyday user in the ecosystem, like what would be, if you're running a wallet or a DeFi app or what have you, what would be the sort of, as Laos sort of comes online, what would you, and this is to anyone really, what would you sort of say the main advantages, both sort of technically and perhaps in a sort of business context as well, for the normal Cardano community member or person who's developing their business with us?
I can take that. I think for the end consumer, for the end user of wallets and so on, I don't actually think there's big of a difference aside from perhaps experiencing less of a congestion or anything. So they can maybe use more complex and better dApps because now they're capable of making use of layers, and they may not be as, like, if they submit transactions, they may not be congested because we can handle more traffic. So things like that. So it's not, I think it's not that advantageous for the end user specifically, but definitely for builders that can maybe offer new ideas, new products, while we also preserve some of the changes for like wallets. I think for instance for wallets, I think the changes are actually very minuscule. So that's one of the big upsides of the proposal compared to what we have discussed in the research paper.
Okay, great. We're still. I encourage you to submit a question if you have one. I've got another one then, and it's really about the integration path. And this might be a question for engineering more than innovation, but what would you say would be the practical steps for deploying Laos on mainnet? And will they be incremental, as it were, or will it be sort of milestone based or fork based with sort of major upgrades?
Brian, do you want to take this? I know you have some opinions on this regarding testnets.
Yeah, so I should say there is a public roadmap that's being worked on, so you can visit the Laos repository and project and look at the roadmap, and you can contribute to that. So, we have Discord channel, these monthly meetings. There was actually earlier this week in France, there was a node diversity meeting where there was a lot of discussion of Laos, coordinating among all the different nodes, not just the Haskell node, how to start getting it deployed. And so there's that road mapping is going on. Basically, there's a implementation phase. It's likely there would be a single hard fork for Laos. For this version of Laos, future increments, would be other hard forks, and that there definitely will be like there was SanchoNet for governments, there will be a special purpose test net for Laos, so people can really kick the tires and hit it hard. And we also want on that, and also on preview and pre-prod, to incentivize people when Laos reaches those stages to run high throughput. Like we want complex dApps, high Plutus budgets, airdrops, and all those things on the testnet to really show how Laos works. And then in terms of deployment onto mainnet, Laos is nicely tunable. So the protocol parameters can be set so that throughput is increased in baby steps, so that on day one, the parameters might not be set for the highest possible throughput, because that could overwhelm some of the infrastructure, the third-party infrastructure. But that can be very easily, just through protocol parameter updates, increase the size of the endorser blocks as the community and all the infrastructure gets comfortable. So a lot of work going on already on the nodes coordinating, and the indexers are going to have to upgrade their infrastructure most. Wallets, command line tools, things like that are going to have a minor impact And then, as Will said, the users will not have to change how they think about LAS, other than they're going to have more opportunities, like more interesting dApps, seeing less congestion. So it should be exciting for everyone.
Great, great. I've got two more questions, if I can, before we wrap. And the next one is to you, Georgios. Could you talk a bit about how research has worked with innovation and supported the innovation work stream? And I guess that then extends to how do you envisage, how does the innovation team envisage supporting the engineering team, so we have that coherency as we go through?
Yeah, thanks for the question, Fergie. Can you hear me well now?
Yep.
Okay, good. The initial step of innovation was, the research paper. So the research paper had fundamental concepts outlined and had an initial proposal. And then what we did together with engineering was, see what are the real world constraints, do simulations, see where what the research approach missed, what constraints it didn't consider, but we should consider now, and then reshape, change the protocol, and the protocol has changed a lot based on these constraints, right? So having in place the right language to talk about, the right language to view the design space basically allowed us to quickly move, in different directions based on the different constraints we faced. And in fact, this wasn't part of this talk, but in fact, we changed our opinions a lot, and we were able to move a lot in the design space to find, this, optimal assumption point with the time. There are other optimal points in different time, but this is one optimal point, and it's, as we've said, it's optimal in the sense of time to market, and it's the fastest and the cheapest, in some sense, thing to do to increase throughput substantially.
Okay, great. And I know that the engineering team started hiring and sort of putting resourcing in place a month or two ago, so that there was a sort of a clean handover, as it were. What sort of, how's that gone, and what sort of support do you envisage that they'll require going forward, William or Brian?
Yeah, I think it's a process. So we have actually onboarded Sebastian probably as one of the key members earlier or mid of this year. So he has been a key player, proposing new ideas, simplifying things. So I think this transition has been ongoing, and now he's kind of preparing his team to get up to speed. And from what I can tell, they're in a very good place. He's also very satisfied with our proposal. And now it kind of depends on a few more reviews. So we're constantly observing the SIP in terms of what people have to say, what kind of improvements they want us to make or consider, maybe rephrase or clarify things. And I think it probably takes maybe 1 or more 2 weeks until we reach a point where we can maybe push the SIP into maybe some approval state if everything goes well. And from there, I think it's from our side, it's mainly up to supporting them and see what they need. If they need more knowledge, more simulations. But I think so far everything looks good. It's just a process of not just 1 day or a week, but probably months to hand things over.
Great, thank you. And then lastly, just to finish, and this is probably more at a personal level as much as anything, what perhaps were the toughest times and the most challenging times in the process, and then conversely, what would have been the most rewarding times as you worked on the on LAS over the last year or more?
I think it's probably different for each of us. So one thing that I've observed was that at different times, different people were in high demand. So they had to deliver a lot of work in a shorter time frame because people were depending on them. And for me, one of the toughest times was probably writing the SIP for the last month. So I've received a lot of input and tried to stay up to date with things that have changed. But I know it's been different for Brian and Jurgis and other people on the team, so maybe they speak for themselves. But yeah.
Yeah, I think for me, the hardest time, like there's just an incredible amount of like intellectual energy and work going on the project. And sometimes it's moving forward on all fronts, and there are a lot of really deep discussions going on. And it's been the hardest for me when it's just overwhelming to track all these technical details all at once. Fortunately, that was bursty, so most of the time, you know, I could keep up. But when we have 7 or 8 people contributing really good ideas to solving a bottleneck, that takes a lot of intellectual energy. And I think for me, since I was doing this simulations, the most exciting part was just seeing the protocol working, like seeing the transactions move, you know, getting these great numbers for performance, watching it resist attacks. That was a very tangible reward.
Yeah, and I'll give the research perspective. So from a research perspective, it's always interesting, you know, to see real world constraints come into theory and trying, you know, to model this and think how do they, you know, fit in the as I said, in this design space. But I would say, but it's also really the, you know, it's on the one hand it's very, you know, fun and nice, but it's also very stressful because now, you know, you're suddenly your protocol is no more, you know, the optimal protocol under the constraints described. So now you have to again move in this design space and find a protocol that actually can deliver with respect to these constraints. And throughout the year, we've had, I don't know, at least 3 times that, you know, something that wasn't that much anticipated came up, and we had to, you know, really change, you know, the protocol in a fundamental way.
Good.
Luckily, we could deliver in them. So
It's good. Well, congratulations on the handover milestone. That it's a notable achievement. So we'll finish there. Thank you, William, Brian, and Georgios. Thank you to Agalos as well, and thank you to all of you for making the time this afternoon. We'll actually be back on the 7th of October for Interchains. We've got a really exciting lineup there, and we'll probably return to our sort of more conventional format of an initial research presentation and a roundtable from stakeholders from the Cardano community. So we look forward to seeing you then. We'll be writing up on the IOHK blog. We'll be adding the video to our YouTube playlist, and we'll also be posting on Cardano and other community platforms. So please read up and share when you have the time. All right. Thank you all. Have a great day.